Hi, my name is Shmuel Bialy. I'm a postdoctoral fellow at University of Maryland. And today I want to say a few words on the turbulence chemistry connection and how this relates to the magnetic fields and the density structure of the interstellar medium. This is based on a series of several papers, first from 2017 and until more recently, about the atomic to molecular transition, other molecules, and then finally what I'll touch about the connection between the driving scale of turbulence and the decorrelation scale of the density field. And the basic idea is as follows. We have turbulence in the interstellar medium, magnetized turbulence, and we want to understand its properties, like what drives it and what's the scale of the driving process of turbulence in the ISM. And the turbulence, once it becomes supersonic, it produces density fluctuations. And now these density fluctuations, they affect the chemical structure, affect the chemistry, formation, and destruction of different molecules. And now we can reverse the arrows, and if we observe different chemicals, molecules, and atomic species, we can deduce potentially the density structure and turbulence. And of course, the magnetic fields come here in both cases because the magnetic fields is tied into the driving process of turbulence, and also it affects the density field when you observe it along the line of sight of the B field or perpendicular, as we'll see. So this is basically the idea, and the question we want to answer is what drives the turbulence and what is the driving scale. And we'll see that the B field comes in both cases. So to try and answer this question, we ran a series of simulations, magnetohydrodynamic simulation of driven turbulence, periodic boxes in different resolutions. Here, the fiducial case is 512, but we also have higher resolutions. And the simulations are characterized by the driving scale, sonic Mach number, and alphenic Mach number. This defines the density field. Now, once we have the density field, we irradiate the simulation with UV and cosmic rays, and in post-process, we calculate the abundances of different molecules, such as H2, and different molecular ions that are sensitive to, for example, cosmic rays and a UV field. And now, once we have these calculations of the molecular abundances, then we can compare this with observations and say something about which models of the turbulence are more compatible with the observed abundances and which are less. That's the idea. I'll just briefly mention a few results, and that connects two things. One is what the effect of the sonic Mach number and the decorrelation scale on the abundances of chemical species. And the second thing that is more related to the magnetic field and to based on a recent study is the decorrelation scale driving scale relationship, and that touches to how can we constrain the driving scale and the driving process of turbulence. So let me first start with number one. So what's the effect of the sonic Mach number? Here we see two simulations with different sonic Mach number, subsonic and supersonic. These are density slices. And what I show here is the calculated column density of atomic hydrogen. So this already includes all the effect of the UV absorption through the cloud by dust, and the formation of molecular hydrogen and destruction of molecular hydrogen by the UV. And what we see is that for subsonic simulations, the atomic hydrogen probability distribution function is much narrower than for supersonic. And this is understandable because what is happening is that as we increase the sonic Mach number, density fluctuations become stronger. We have a broader PDF for the density field. This is a known result. And this in turn also affects strong fluctuations in the formation and destruction of molecular hydrogen, and therefore makes the PDF of the column density of H1, this is the PDF of the column density of H1, also broader. So basically, stronger density fluctuations are present when the sonic Mach number is large, and these density fluctuations in turn reflect in the chemistry and produce larger dispersion of the column density. So potentially we can observe the PDF of H1. This has been done for many clouds, and then deduce the sonic Mach number. However, it's not the only parameter that is important. In fact, the other parameter that is important, and that's what makes this so interesting, is the decorrelation scale. And what do I mean by this? The density fluctuations are not only described by their magnitude, but how strong they are, but also by their size scale, if they're small in size or large in size. And this has a big effect on the chemistry and the observations of H1 in this example, but also other molecules. Because what happens is if the density fluctuations are very small, then there is an averaging effect. And along the line of sight, when you integrate everything, you get a smaller dispersion for the column density of the molecule of interest. However, if the density fluctuations are large in their extent, then you don't have this averaging effect, and the PDF of whatever you observe is typically wider. And this is what we see here. This is the observed, this is the column density again of H1, a two-dimensional map projected onto the simulation for large the right and small decorrelation scales, and this is the corresponding PDF. And you see that when the decorrelation is large, the PDF is wider because of this effect. You don't have the smoothing. On a small decorrelation scale, when the fluctuations are small in their size, then you have smoothing along line of sight. This is for the same sonic Mach number. So the PDF of the density field is the same. It's just the smoothing effect that reduces the PDF here and there. So in other words, what we can say is that if we observe a PDF of H1 or some other molecule, by the dispersion in the PDF, say the standard deviation, we can deduce the sonic Mach number, but the other parameter that is also important is the length scale of the fluctuations, which is characterized by what we call the decorrelation scale. And more details you can find in this paper, how we measure the decorrelation scale. And these are degenerate in a sense, but there are other ways to deduce the sonic Mach number, for example, from the spin temperature. What is interesting is this second parameter, the decorrelation scale, is related to what we're after for the driving scale, or the question, what drives turbulence in the interstellar medium? And this is the next thing I want to talk about, the connection between the decorrelation scale, LDEC there, and here, and the driving scale of turbulence. So to see if there is a constant relationship or if it changes with parameters, say the sonic Mach number or magnetic field orientation, what we did is we ran several simulations, MHD simulation of turbulent boxes driven on different scales. So this is a K drive of 2.5, so half box kind of scale. This is a smaller driving scale and yet smaller driving scale. And also at different resolutions to make sure we converge, and observe these simulations in different orientation relative to the B field. So here the B field goes into the screen, and here it's in the plane of the screen. And by eye already you can see that here in the upper panels, the density fluctuations are rather isotropic. And here they are highly non-isotropic as expected. And in fact, the density is more compressed when goes along the magnetic field lines here. These filaments are thin when perpendicular to the field lines. And what we want to do is to measure the typical size scale of these density fluctuations and compare it with the driving scale on which we drove the turbulence, which we know. And this is what we find. And it's actually very interesting how we measure the decorrelation scale. There are different methods, but I won't go into details, just check out this paper from 2020, where we describe an interesting method for how to measure the scale, the typical scale of density fluctuations, or what I call LDAC. What we find is that the decorrelation scale is proportional to the driving scale, as might be expected, because it's results, the density fluctuations results from the driving. We find that this indeed occurs numerically in our simulations. The ratio is what I call phi. If you are perpendicular, if you are parallel to the B field lines, there is more compression. Compression is more easily achieved, and the ratio is smaller. So the density fluctuations are smaller in size, and they're typically 10% of the driving scale. And when you observe perpendicular to the field lines, then there is more scatter, and typically the fluctuations are also larger, and this is what we see here. On the mean, it's about 0.2 something. And these different symbols are different simulations with different sonic Mach numbers, resolutions, and yes, sonic Mach numbers and resolutions. So this is basically the result. And the idea is now that, again, just to connect back to the previous slides, is that the turbulence is described by the driving scale and other parameters such as intensity, mode, and the B field. And then the turbulence in turn results in the density field. The density field is described by the decorrelation scale, and this is the relationship between the two, the decorrelation scale and the driving scale, and the orientation matter because of the B field, as we saw. Finally, the density field dictates the abundances of chemical species. This is something we can observe, and then from the observations, the idea that we can deduce the density field and back the turbulence, where the relationship between the decorrelation and driving scale is critical here for this route to be achievable. Of course, there's many other yet steps to do this more robustly, but this is basically the idea, and this is a key relationship to be able to make it from the observations to deduce the turbulence and the density field. I'll just mention this. I won't go into detail because I don't want to this talk to become longer. But we have some first observations, such comparison we made. This is described in this 2019 paper, where we observe argonium H+, OH+, H2O+, and atomic hydrogen, and we compare the observations from Herschel to models with different sonic Mach numbers and driving scales, and we favor models that have large driving scale and supersonic turbulence, which relates to turbulence that's driven on large, perhaps galactic scale processes. So I just want to summarize with this diagram again, where we connect turbulence, density field, and chemical abundances. The B field plays a key role because of the non-isotropic effects on the density field as well as on turbulence driving, and the connection between the decorrelation and driving scale is important in order to be able to make it from observations of molecules to results and understanding of the density field and turbulence in the interstellar medium. So check out the paper for more details from 2020 with Bialy and Burkhart and myself. And thank you very much. Looking to talking to you soon.